Welcome to Basic Mathematical Analysis class. Today we will discuss Cauchy's Theorem on limits. First we will study the first theorem, Cauchy's first theorem. Cauchy's first theorem. Let xn be a sequence converges to 0, and let you got another sequence yn which is equal to x1 plus x2 plus extra plus xn by n for each n belongs to n. Then yn also converges to 0. So this is the thing we want to prove. That is Cauchy's first theorem. First theorem states that let xn be a sequence converges to 0, and let yn equal to x1, x2, extra xn by n for each n belongs to n. Then yn is also converges to 0. So let us see how we can prove it. Proof. Take any epsilon greater than 0 since xn is given to be as converges to x, right? Sorry, converges to 0. There exists converges to 0. There exists some positive integer, a positive integer, let us say such that modulus of xn is less than epsilon by 2 for all n greater than or equal to this follows from the definition of convergence. Also, we know that every convergence sequence is bounded, right? Every convergent sequence is bounded. So what we will have? So I can have a real number such that mode of xn is less than or equal to that real number. So there exists a real number r greater than 0 such that modulus of xn such that modulus of xn is less than this r, right? Less than or equal to r for all n. By making use of these two ideas, we will prove that this sequence is also converges to 0. Now choose n1 Now choose n1 such that your n1 is greater than m, and you are selecting r by n1 is less than epsilon by 2m. Let us see why we are selecting like this and all, right? So let it be the, so we don't know why we have selected like this. So such that this we can discuss, okay, why we are selecting like this. Okay, now choose an n1 such that n1 is greater than m and r by n1 is less than epsilon by 2m. Then for every n greater than n1 or equal to n1, modulus of yn, that's equal to modulus of x1 plus x2 plus extra plus xn by n. This value is less than or equal to, I can put this as, I'm splitting this up to m terms, then m plus 1 to n terms. So modulus of x1 plus x2 plus extra plus xm by n plus modulus of xm plus 1 plus extra plus xm plus or n, right? xn by n. Why I am splitting like this means from here onwards, from this side onwards, that is this term onwards, I know that this value is less than, see, we are having n greater than m, this value is less than epsilon by 2. So I can use it here. That's right. Now this value is less than or equal to, I can split it further, right? Mod x1 plus mod x2 or by n plus etc. mod xm by n plus mod xm plus 1 by n plus etc. plus mod xn by n. Now from here onwards, I can use that quantity, right? So how I can use it? Now this part is less than or equal to, suppose I am taking this term, okay? This every term is less than or equal to, this term I am taking as such mod x1 by n plus mod x2 by n plus etc. plus mod xm by n. I'm taking this as such, okay, as such. Now plus xm plus 1 by n is there. So I know that modulus of xm plus 1, see from here, for every n, see from here, what I am having is for every n greater than m, mod of xn is less than epsilon by 2. So I can replace that with epsilon by 2, but 1 by n is outside, right? So I'm putting this 1 by n into epsilon by 2 plus etc. plus epsilon by 2. How many numbers of epsilon by 2 are there? M or n minus m, right? Total is m, n. So up to here is m terms. So n minus m. So this reduces as plus this term I am writing. You have said that n minus m by n times epsilon by 2, right? Now what about this term? For this term only, we have selected our inequality like this inequality, right? Epsilon by 2m you have selected. Each of the sequences are less than r, right? So I can write this as r by n, first term, plus this term again r by n, plus etc. again r by n terms, right? So totally how many terms are there? How many terms? M terms, right? So m times I will get this equal to m times r by n plus n minus m by n times epsilon by 2, right? Now what about m into r by n? R by n1 you are selected. See, n1 greater than m you have selected, so it should be satisfied. So this we can replace with epsilon by 2m, right? So this I can replace with, suppose we have denoted that as this as some a means r by n1. So m is already there, so you can replace that with, that's less than or equal to m into epsilon by 2m will come, right? Plus n minus m by n into epsilon by 2. So what it will reduces as? So it will reduces as 1 n should be there, no? M times r by n. So that r by n epsilon by 2m. Yes, I have put. Now this quantity means I'll get this as this is equal to epsilon by 2, right? Epsilon by 2 plus n minus m by n. What it will reduce as? It will get less than, anyway it should be less than epsilon, right? So we can have this from A, right? Now this quantity you will get this value is less than, so we get this value is less than epsilon. So what does this implies? This implies your sequence, that is yn, that is sequence x1 plus x2 plus extra plus xn by n. This is the nth term of the sequence. Is also converges to 0 because you have taken modulus of yn, which is exactly modulus of yn minus 0, and that is less than epsilon. So it follows. Next we are having a corollary 3.2.10 corollary. If xn converges to x, then x1 plus x2 plus extra plus xn by n converges to x. Converges to x. If xn converges to x, then x1 plus x2 plus extra plus xn by n also converges to x. So how to prove this? How to prove it? This corollary. It's very easy one. Proof. Suppose your xn converges to x. Now this implies xn minus x, if I'm taking the sequence xn minus x, which will converges to 0, right? Now apply the previous theorem, right? Apply the theorem 3.2.9 to the sequence yn equal to xn minus x. Then we get what do we get? Xn minus x. So x1, x2, x3, etc. minus x will come. So we get that will converges to direct application x1 plus x2 plus extra plus xn by n, which converges to x. Exactly, you will get this sequence xn minus x converges to 0, you will get. So in particular this sequence will converges to x, you will get. Next we are having an example. Example 3.2.11 example. How we are making use of this theorem? It's exactly a question itself. Show that limit of 1 plus n minus 1 by n into a plus extra plus 1 by n into a raised to n minus 1. This equal to 1 by 1 minus a, where condition is modulus of a is less than 1. So we want to prove that 1 plus n minus 1 by n into a plus extra plus 1 by n into a raised to n minus 1 is equal to 1 by 1 minus a, where modulus of a is equal to 1. How we can prove this? Any idea? So we can write this as a question itself. Now solution. First of all, we know the geometry progression for this, right? First we are writing that one. So 1 plus, we have 1 plus a square plus extra plus a raised to n minus 1. It should be equal to 1 minus a raised to n plus 1, right? So it should be n by 1 minus a. And limit of a raised to n equal to 0. What's the reason? Since modulus of a is less than 1. So when you have go on power of this, means it should be less than 1. Which should be less than 1. So let xn equal to 1 plus a plus extra plus a raised to n minus 1, right? Now limit of xn. Now limit of this xn, we have already seen, right? This is equal to 1 by 1 minus a. What's the reason? When limit of n you are taking means n tends to infinity, so you'll get an infinite series. Now sum of the infinite series and all you have studied, that is 1 by 1 minus a. Therefore, what you're getting, x1 plus x2 plus etc plus xn by n. This sequence is equal to what it should be. This sequence, see, we want to find what is this sequence, right? This sequence should be exactly 1 plus n minus 1 by n into a plus etc plus 1 by n into a raised to n minus 1. Is it clear? The sequence is nothing but this. Okay, let us examine. Okay, how we will get this. So, okay, we will have a box here and I will explain to you. Okay, how we are getting this one. Okay, see how you got this one. I am explaining here. We have x1 equal to 1, right? X and this sequence only I am taking this sequence, right? So x1 equal to 1. What about x2? x2 equal to, from this sequence, having a difficulty in understanding the sequence. See, this sequence is nothing but, I'm writing, okay, let us see what this happens. See, exactly, the sequence means you're having your yn, right? I'm writing yn equal to x1 plus x2 plus extra plus xn by n. Or you take no need of taking n itself, you take like this. Okay, now what about y1? y1 means only n equal to 1, right? So x1, y2, n equal to 2, so it should be x1 plus x2, right? Or I'm taking xn equal to a, no, so this term only I should consider, right? So I should put this as 1 plus a, right? So it should be 1 plus, written, yeah, everything in terms of a, no. So I should have this as xn is given as, oh, I have made a mistake here. It's given that xn, not yn. Okay, so let me copy that here. See, this one only I'm saying. This is your xn, right? This xn only I'm copying here. So xn is given as 1 plus a plus extra plus a raised to n minus 1 type, right? So my x1 should be equal to 1, no doubt. X2 should be equal to 1 plus a. X3 1 plus a plus a square will come, right? Etc. Like that, xn means I will get 1 plus a square plus etc. plus a raised to n will come, right? Xn a raised to n minus 1, right? Exactly, a raised to n minus 1 will come. So this is my xn. Now suppose I want to add this 2 means what I will get. Okay, let me draw here. Suppose I want to add this, what I will get if I am adding these two. Now this x1 plus x2 plus extra plus xn, that's equal to, I should add these terms all together, right? So it should be 1 plus 1 plus 1 plus 1 plus 1. How many times? N times. So it should be n, right? Plus next term, how many a should be there? Only in the first term there is no a. Remaining n minus term containing a. So n minus 1 into a. Similarly, how many terms containing a square? N minus 2 into a square, right? Plus extra plus last term should be 1 into a raised to n minus 1, right? Now therefore this divided by n, therefore x1 plus x2 plus extra plus xn whole divided by n, what it should be? What it should be now? This should be equal to, this is equal to, I should divide everything with n. So n by n 1 plus n minus 1 into, sorry, n minus n by a into a plus n minus 2 by n into a square, right? Plus extra plus last term is 1 by n. So 1 by n into a raised to n minus 1. You have got exactly the same, right? From here to here you want to consider. It's not coming. So here to here. So you will get exactly this one, right? Then by using above theorem, then by above theorem, what we will get by above theorem? We get this sequence, that is 1 plus, this means also converges to x, right? That means we get 1 plus n minus 1 by n into a plus etc. plus 1 by n a raised to n minus 1. This term will also converges to x1, x2, x3, x4. That is a 1 plus a square plus a cube plus extra plus a raised to n, right? That will also converges to 1 by 1 minus a. So we have proved that theorem. Now we will pass to Cauchy's second theorem on limits. Now Cauchy's second theorem on limits 3.2.12, Cauchy's second theorem on limits. let xn be a sequence of positive terms such that your xn converges to x, then what you're having is x1, x2, etc. xn, all thing raised to 1 by n also will converges to x. So we want to prove that xn is a sequence of positive terms such that xn converges to x, then x1, x2, x3, etc. xn raised to 1 by n, that will also converges to x. It's not the product. Okay. So proof. First we will make use the idea of the inequality of geometric progression, geometric mean, arithmetic mean and harmonic mean. Let Gn equal to this term x1, x2, x1, x2 product xn raised to 1 by n, and an equal to x1 plus x2 plus extra plus xn all divided by n, and hn equal to harmonic mean, right? So that is n by 1 by x plus etc plus 1 by xn, right? Denote respectively the geometric arithmetic and harmonic mean of x1, x2, extra xn. Then what's the inequality connecting these three? Which is the least one? Harmonic mean, right? So hn is less than or equal to gn, which is less than or equal to an. So arithmetic mean is going to be the highest one. Now our aim is to show that this gn, right? So x1, x2, x3, etc. xn raised to 1 by n. That is our, so previously I have said that there is a comma, so there is no comma here. So okay, I'm writing x1, x2, etc. xn is right. Now our aim is to prove limit of this gn equal to x. So we will examine this by two cases. Case 1, let x equal to 0. What will happen? If this limit is equal to 0, what will happen now? This x equal to 0. Then, what about the arithmetic mean? Then arithmetic mean should be equal to 0, right? So if x equal to 0, then by Cauchys first theorem, first theorem. What is Cauchy's first theorem? Cauchy's first theorem says that whenever you are having a sequence xn converges to x, then x1 plus x2 plus etc plus xn by n also converges to x. This was Cauchy's theorem. Then by Cauchy's theorem, what you will get? On limits, we have limit of an equal to 0. So what will happen? An equal to 0. See, all are positive quantities. So Hn should be a 0, right? So thus 0 less than Gn less than An. Then what we can use? This An is equal to 0. Now, by Cauchy's theorem, what is Cauchy's theorem? Cauchy's theorem, 3.2.7, we get limit of Gn equal to 0. So what you got? Limit when x equal to 0 means we are getting limit of Gn is equal to 0. Now case 2, x is greater than 0. Then limit of 1 by xn, that's equal to 1 by x, right? Since x is not equal to 0, we can apply this. So by Cauchy's first theorem, then by Cauchy's first theorem, what do you get? Sum of this by n, right? Limit of 1 by x1 plus 1 by x2 plus etc plus 1 by xn, or think by n equal to 1 by x, right? To 1 by x, right? Thus what we are getting? Thus limit of an is equal to limit of hn. Hn means exactly opposite of this, right? Reciprocal of this. Hn is equal to x. Hence by Cauchy's theorem, we get limit of Gn is equal to x. Thus in all cases, this we have proved. Now we have got a corollary, 3.2.13 and 3 corollary. If xn is greater than 0 for all n belongs to n, and limit of xn plus 1 by xn, limit of xn plus 1 xn, that's equal to x, then limit of xn raised to 1 by n is equal to x. So it's proof. So here what we want to prove? we have got a sequence in every term is greater than 0 for all n belongs to n, and limit of xn plus 1 by xn is equal to 0. Then limit of xn raised to 1 by n is also equal to x. To prove, let an is equal to xn by xn minus 1. Taken like that for n greater than or equal to 2, and a1 equal to x1. Since limit of xn plus 1 by xn, this is given to be as x equal to x. Now what about this sequence limit? That also equal to x, comma, limit of an is also equal to x. So here our sequence is like this. Our sequence okay, our sequence is I'm having a1 equal to x1, a2 equal to this, following this formula, an equal to xn by xn minus 1. So a2 equal to x2 by x1, a3 equal to x3 by x2, right? So like that I am continuing. Then an equal to similarly xn by xn minus 1, right? So therefore, suppose I am having the product a1, a2, a3, extra an. So this should be nothing but x1 into x2 by x1 into x3 by x2 into etc. Last time should be xn by xn minus 1. So this term should be xn minus 1 by xn minus 2. So this will reduce as, see, x1 x1, x2 x2, x3 x3 will come, xn minus 1, xn minus 1. So at last this only this term will remain. So that should be equal to your xn, right? So this was your sequence. Okay, now hence by Cauchy's second theorem, hence by Cauchy's second theorem, but you will get product of this, right? Theorem on limits 3.2.12. What do you get? A1 into A2 into extra an whole thing raised to 1 by n also converges to, that is equal to, now we have got it as xn. So I'm writing xn raised to 1 by n, which also converges to x, since your xn converges to x. So what you have proved? You have proved now xn raised to 1 by n also converges to x. Xn raised to 1 by n also converges to x. Now we are having an example, 3.2.14 example. Show that limit of n raised to 1 by n equal to 1. Now here we will define a sequence define a sequence xn as follows. Let xn equal to n by n minus 1 for all n greater than or equal to 2 and x1 equal to 1. So what do we get? So x1, x2, etc. xn all thing raised to 1 by n. But it should be in the same way you can have. So in the same fashion, it will have only the last term only will pertain. That is n raised to 1 by n. Right? Since limit of xn that's equal to limit of n by n minus 1. Right? This is equal to 1. This we have seen, right? Limit of n by n minus 1. How you have found this? That's equal to limit of 1 by 1 minus 1 by n you will write. Now as n tends to infinity, 1 by n will reduce as a 0. So limit will reduce as 1. So we are making use of this fact here. Okay, this we are using here. So we get limit of n by n minus 1 is equal to 1. Then by Cauchy's second theorem, then by Cauchy's second theorem, on limits, we get limit of n raised to limit of xn, right? So limit of n raised to 1 by n will converges to or this is equal to 1. So in today's class, we have discussed Cauchy's first theorem and second theorem, and we have seen two examples for that too, right? And we have seen some of the corollaries too. So Cauchy's theorem, Cauchy's first theorem says that when xn sequence converges to 0, then x1 plus x2 plus etc plus xn by n also converges to 0. Then second and its corollaries are there. And Cauchy's second theorem says that when you are having xn sequence positive terms such that xn converges to x, then x1, x2, x3, etc. xn all thing raised to 1 by n also converges to x. So hope you understood today's class. If you are having any doubt regarding this, please ask me through your classroom. So thank you for your patient listening. Thank you.